Geometry progress check for GCSE Foundation. This is 4.1, focusing on shape properties and calculations. The first question is asking, this shape can tessellate, so it is a statement. Is this statement true or false? So we've got a pentagon and we've got to work out whether it tessellates. A shape that tessellates can have many of them fitting together with no gaps. So trying to draw some pentagons, and then if I try and draw another one next to this, as you can see, pentagon does not tessellate. So there would be gaps in here and there. So you could try and fit these around, but a pentagon does not tessellate. So this is a false statement. Shapes that tessellate are rectangles, would have squares as well. Not drawing them properly. We have hexagons, octagons as well. So think of the shape of the tiles that you might have in your kitchen or bathroom. What kind of shapes are they? Typically rectangles, squares, hexagons, octagons as well. So these are the kind of shapes that tessellate. The next question is, which shape is C congruent to? So to be congruent means it's going to be identical. It's going to have the same size as well. So if I look at these ones, I have A is hexagon. We've got a pentagon for B. C is a pentagon as well, and D is a pentagon. Now the two that are identical are these two, which is C and B. So C is congruent to B. D is also a pentagon, but it's not congruent to B or C because it's larger. So D is similar, not congruent, it's similar to C and B. What is the order of rotational symmetry for this regular hexagon? A shape has rotational symmetry when it can be rotated and it still looks the same. The order of rotational symmetry of the shape is the number of times that you rotate the shape around a full circle and it still looks the same. Let's see what this means. So I'm going to make a copy of this hexagon and then we'll paste it. So we'll place this on top. So I'm going to rotate the shape on top, but we'll mark one of the corners so that we know where we started. So at this moment, this one is here. So if I rotate this shape to the right, then that corner will be coming here. So far we have the order of rotational symmetry being 1. So we've come to a point where the shape on top looks exactly the same as the shape underneath. So it fits into place. Now we'll move this again to the right, and that corner has now moved here. So this is order of rotational symmetry number 2. Once more, and this is 3, 4, 5, 6. So 6 would be the answer. Now you've got to check that you didn't really count this when you started. So if I counted this corner, this vertex, when I started, I don't count it again when I come full circle. Generally, the order of rotational symmetry for regular shapes is equal to the number of sides or vertices, corners. However, there are exceptions, just like with circles, which I'm going to show now. So a circle, you can rotate as many times as you wish, as many degrees as you wish, so you can keep rotating. And it falls into place each time. If you keep doing this in small steps. So a circle has an unlimited order of rotational symmetry. Now, the minimum number of rotational symmetry that a shape can have is 1. So any shape would have 1, at least 1. So if I quickly draw an irregular shape, and this is the starting point, for example, you can rotate the shape and no doubt it will come to this point after you've rotated it 360 degrees. So the minimum order of rotational symmetry number would be 1. What is the name of this shape? We decide the name of the shape based on the number of sides, and this one has 1, 2, 3, 4, 5 sides, so it is a pentagon, not a regular one. So this is irregular. So if you want to be more specific, you can write irregular pentagon, but it is a pentagon. The next question is asking, look at the solid, how many vertices does it have? So vertices are the corners, and as you can see, this has a corner here, another one here, another one. So there are 5 in total. Now we have, here is the plan view, front elevation and side elevation of a cuboid made from 1 centimeter cubes. So if I am to draw the shape, how it looks like as 3D, we'd have approximately, this is not a perfect drawing of it, so we have the plan view, so the shape at the top, which is 3 by 3. Then we have a front elevation, which is 3 at the top, and then going 2 down. So we'll keep the lines parallel. Can retry this last bit. to make it more accurate. And we have the side elevation, which has 3 centimeters at the top, and then 2 going down. This is not perfect, but gives you an idea. So this solid then has these dimensions. There is 3 times 3 times 2. Or if you want to think of it as length, width, and then height, that still is 3 times 3 times 2. 3 times 3 is 9, times 2 is 18. What's the unit? That is centimeters cubed. So option C is the correct one. Now we have a net. Circle the name of the solid formed by the net. As we can see, there is a circle at the top and a circle at the bottom. So if I draw these, and then there is a rectangle that connects these two, and that is a cylinder. Now in this other question we have, this shape is made by cutting out an equilateral triangle from a square, like shown in this picture. So we've cut out an equilateral triangle, which means having equal sides. So there was a triangle here which has equal sides, and it's cut out from a square. So a square, as we know, has equal sides as well. So this is 5 centimeters, this is 5, this is 5, this is 5. And since this triangle is equilateral, that means that this is 5 as well, and this is 5 centimeters. So this is going to help us work out the perimeter of the new shape, which is made of the two of the shapes put together. So we have this being 5, 5, 5, 5, 5, 5, 5, 5. Make sure you do not count this, because a perimeter is about the rim going around. So it's lots of 5s, so I'm just going to count them. There's 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 5 is 40, and it is centimeters. So the answer is 40 centimeters. In this question, we have to find the missing length in this parallelogram. So we have a parallelogram, and we're given this dimension, but we haven't got the height. Now, we should remember that to work out the area of the parallelogram, we just need these two dimensions as shown in red, because this is very similar to a rectangle. So this part of the shape would be able to fit in here, creating so a rectangle. So we can treat this as a rectangle. Now we know that the area is equal to 52 centimeters. So we'll show the area in a different color. So if the area is 52, which we find by multiplying 8 with this number that is missing. So we need to find that number that is missing, which we can by dividing 52 by 8, and that is 6.5 centimeters. Now we have to describe fully the single transformation which maps triangle T to triangle V. So we're getting from this to this. I can see that they are mirrored. So this must be a reflection. And the line's got to be right in the middle between them two. I think it is this line, but I can double check by looking at the distance between corners. So top corner here, top there. Let's see. So there is 1.5, and there is 1.5 on the other side. Let's have a look at the other corners. So there is 1, 2, 3, 1, 2, 3. So this shows that this is a reflection on line y equals x. How do I know? Because when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3, and so on. But this one here acts as a mirroring line. We now have to convert 12.4 squared meters into squared centimeters. Now, one thing to remember here is that we're not converting meters to centimeters, but squared meters to squared centimeters, and we'll see what this means. So if we have a meter here, so there is a square, 1 meter, 1 meter, 1 meter, 1 meter. Okay. What does this mean in terms of centimeters? So 1 meter is 100 centimeters. So this means 100 times 100, which is 10,000 centimeters squared, or squared centimeters. So if to convert from meters to centimeters would have to multiply by 100, when converting from meters squared into centimeters squared, we'd have to multiply by 100 squared, which is 10,000. So I'm gonna go and do 12.4 times 10,000, which means I'm gonna move the decimal point 1, 2, 3, 4 places to the right. So we go from this point, we have 1, 2, 3, 4. So the answer should be 124,000 centimeters squared. Now we have the radius of the top of a circular table is 40 centimeters. So the radius is 40 centimeters. Work out the area of the top of the table using pi equals 3.14. So we have two formulas for a circle. We have the circumference and the area of a circle. Area pi r squared and circumference 2 pi r. So pi r is not changing, it's just the 2, whether you put it at the front or at the end, at the top, like in here. In this case, we're going to use the area formula. So we have A equals pi r squared. Substituting the values, pi in this case has to be 3.14 times r, which is 40 squared, which is 3.14 times 40 times 40, and this is equal to 5,024 centimeters squared. We now have to work out the bearing of A from P. So it is from P, that's our starting point. P is point here, so we go up to the north and we go into A, which is here. So we're looking at this angle between them two. And how do we work that out? We know that a full circle has 360 degrees. We have this part which is 138 and we have 120. So 138 at 120 is 258. What we're going to do now, take it away from 360. Okay. So this is 102 degrees. So the bearing of A from P is 102 degrees. One thing to bear in mind though, if the answer was 58 degrees, for example, you need to write it as 058 with 3 digits. Often this is called the 3-figure bearing. So what all that means is having 3 digits. In this case, we do have already 3 digits. So this is the answer. In this question, we'll have to describe fully the single transformation which maps triangle T to triangle S. So I can see that one shape is larger than the other. So this suggests to me that this is an enlargement. We've got to look at triangle T being mapped into triangle S. So although the triangle is getting smaller, this is still an enlargement. So we'll call it an enlargement. Now there are 2 more things we need to find, and that is the center of enlargement and the factor. So to find the center of enlargement, we can use a ruler. I'll bring in a ruler and I'll pick 2 similar points. So 2 corners, 2 similar corners, this one and this one, as you can see. And I will draw a line to connect them. And it will extend it in the grid. So we'll do the same now. We have these 2 similar corners. So we have this one here and this one. We'll connect them through a line. And the other 2 similar corners, as you can see, if we extend the line, we get this point. So this is the center of enlargement. So we'll say with center, this point is 0.03. And factor, which tells us how much bigger or smaller in comparison to the other shape this shape has got. So if I look at the dimensions of the first shape, because this is what we started with, which is going to go 2s. So T has 1, 2, 3, 4, 5, 6 of these squares along this side, and then similar side to that is this one, which has 1, 2. So we've gone from 6 to 2. So 2 is 1/3 of 6. So the factor of enlargement is 1/3. And we can do the same thing with this one. 1, 2, 3. So it's shrunk from 3 to just 1. So again, that shows it's 1/3. Enough proof already that this is 1/3. But if you want to check as well, we have this diagonal across the two squares in here. And there is 1, 2, 3 of them here as well. So finally, this is an enlargement with center 0,3 and factor 1/3. This sector of a circle has radius 13 centimeters. Write the perimeter of the sector to 2 decimal places. So perimeter is about this part here and these two. So we know this is 13, so this is going to be 13 centimeters. And what we need to work out now is this part. We know that this is linked to the circumference of a circle. So if this was a full circle, we'd be able to find the circumference by working out 2 pi r, or pi times the diameter. So pi is given to us in this case, so 2 times 3.14 times the radius, which is 13. This would give us the circumference of the full circle, which is 81.64 centimeters. However, we know that this is not the circumference that we're after. We want only this part. And there are different ways we could work this out. So we could do 115 out of 360 times 81.64. So we'd do 115 divided by 361. We'll show this with a calculator. So 115 divided by 360, and we'll not change this, we'll now multiply it by 81.64. So that gives us this, and we'll just add the 26, 13 and 13. So plus 26. The answer needs to be written to 2 decimal places. So we're going to have 52.08. So we'll write that here. 52.08. and the unit will be centimeters, because that's what we have used. Find the volume of this pyramid. Round your answer to 1 decimal place. So to find the volume of a pyramid, we need to use its formula. What we know is that if I were to make a cuboid with the same dimensions as this pyramid, so it has the same length, width and height, right? The volume of the cuboid would be 3 times the volume of the pyramid. So if you imagine this pyramid of jelly, for example, something that you can squish, you can then fit 3 of them within this cuboid. So the formula for the volume of the pyramid is 1/3 times length times width times height. So this is the formula for the cuboid. You just need to put 1/3 in front, or work out length times width times height and then divide it by 3. It's the same thing. So we'll go, we have 4.5, we have 3.2 and we have 9. If we can't see this very clearly, I can erase bits of it. So we'll go 4.5 times 3.2 times 9, and then all of this will be divided by 3. In this case, we can use a calculator. So we'll get the calculator out. Four 0.5 times 3.2 times 9 divided by 3, 43.2, and the unit is centimeters cubed. We asked to write this to 1 decimal place, and it is already to 1 decimal place.